In this video, we are going to look into infrared or IR spectroscopy. Infrared spectroscopy involves interaction of molecule with infrared radiation. Energy of the infrared radiation corresponds to the energies of bond vibration. There are two types of bond vibration, and they are bending and stretching. They are shown here. Bending involves a change in the bond angle, while stretching involves a change in a bond length. Only vibrations that result in a change of a dipole moment of the molecule can be observed by the infrared spectroscopy, which means that only polar bonds, because they are the ones that have a dipole moment, absorb IR radiation, and so they are the only ones that give absorption bands in an IR spectrum. Intensity of the absorption is directly related to polarity of the bond. So the more polar bond exhibits stronger absorption in the infrared. So for example, hydroxyl group exhibits much stronger absorption compared to CH group because it is more polar. Non-polar bonds, and most of the carbon-carbon single bonds are non-polar, do not absorb in the infrared. Also, some of the carbon-carbon double bonds don't show absorption in the infrared. That's if double bond is symmetrically substituted, because such double bond is non-polar. For example, trans 2-butene does not absorb in IR, but cis 2-butene, which is slightly polar, does show weak absorption. So IR could be used in some cases to distinguish between cis and trans alkene. Infrared radiation is a part of the electromagnetic spectrum with wavelengths between those of the visible radiation and radio waves. Infrared spectrum includes wavelengths from 700 to 15,000 nanometers. Part of the infrared spectrum between 700 and 2500 nanometers is near infrared, and that's part of the near infrared spectroscopy. That's something that is done by specialists, but that's not part of the ordinary common infrared spectroscopy. Typical infrared spectrum consists of radiations between 2500 and 15,000 nanometers. So that's what we call spectral window for infrared spectroscopy. Usually in infrared spectroscopy, we don't use wavelength units. Instead, we use wave numbers. Wave numbers have inverse wavelength units. Wave numbers are inverse wavelength, 1 divided by wavelength. So wave numbers in this case are expressed as inverse centimeters, and spectral window for infrared spectroscopy is between 4000 and 667 inverse centimeters. Here is a sample of an infrared spectrum, and this spectrum can provide us some general information. Bonds in general show as absorption bands in infrared spectrum. So individual absorption band can be associated with particular bonds. Stronger bonds absorb at higher wave numbers and weaker bonds at lower wave numbers. That's a general rule. There are some deviations from it. And as already mentioned, bonds of low polarity exhibit low magnitude of absorption, weak absorptions, while highly polar bonds exhibit strong absorptions. Now, absorptions are additive, so sometimes we can see very strong, very intense absorption band, but that's because there is very large number of bonds of low polarity that are present in a molecule. It's frequently the case with CH bonds. They often exhibit very strong absorption, even though they have low polarity. That's because frequently there are lots of them in a molecule. In analysis of IR spectra, we start at the left, at high wave numbers, and then move to the right towards lower wave numbers. Which means that first region that we usually look at is that between 3500 and 3000 inverse centimeters. There are several important absorptions in this region, and by far the most common one is due to hydroxyl group, to alcohol. So alcohols absorb in this region, and OH is at 3300. Note that OH is strong and broad absorption, and note how it is positioned relative to CH absorptions. CH, because they are numerous in all organic compounds, CH bonds are numerous in all organic compounds. CH are present in pretty much any IR spectrum, and so note where OH is in reference to it. CH is very good to use as a reference point. One exception is when hydroxyl group OH is part of the carboxyl group. Then OH absorption is shifted to 3000 and overlaps with CH. Then it may be easy to miss. First, of course, there is going to be unusual appearance to CH absorption because, of course, it overlaps with OH, and of course, it's going to be accompanied by carbonyl absorption because carbonyl group is also part of the carboxyl group. And here you have the two overlapping absorptions shown separately, OH and CH. Distinguish that from hydroxyketone or ketoalcohol. In case of hydroxyketone, OH and carbonyl absorption will be separate, and OH will be in its usual position at around 3300, and of course keto will show in its usual position between 1800, 1850 and 1650. Another important absorption in this region is NH absorption. NH also appears around 3300, but unlike OH, which is strong and broad, NH is weak and sharp, so completely different shape and easy to distinguish. NH2 group, primary amine, exhibits two separate absorptions. So there are two closely spaced absorptions around 3300, while secondary amine, NH, single NH, shows only one absorption. Another important absorption that is present here is sp hybridized carbon-hydrogen bond. That means hydrogen that is part of terminal alkyne, attached to terminal carbon of the terminal alkyne. That absorption is strong and sharp at 3300. And finally, alkene hydrogen absorbs around 3100. So hydrogen attached to sp2 carbon absorbs around 3100. So as you can see, in this region there are numerous absorptions, but they all exhibit different properties and are very easy to distinguish one from another. Another important region of the IR spectrum is that between 2000 and 1600 inverse centimeters. By far, the most important absorption in this region is that due to carbonyl group. It appears between 1850 and 1650 inverse centimeters, and it is strong and sharp. Usually, it is the strongest absorption in the spectrum. Another important absorption in this region is that due to carbon-carbon double bond. That one is weak and sharp and usually appears around 1650 inverse centimeters. If there is hydrogen attached to sp2 hybridized carbon, then this absorption is also accompanied by CH absorption at 3100 inverse centimeters. Finally, third absorption in this region is due to aromatic ring. This is not single absorption, it is actually composed of several 2 to 4 absorption bands between 2000 and 1600 inverse centimeters, and all of these absorption bands are weak. And then third important region of the IR spectrum is fingerprint region. Fingerprint region is part of the IR spectrum between 1400 and 900 inverse centimeters, and it usually contains a number of complex absorption bands. And this region is very valuable when comparing spectrum of an unknown compound to a spectrum of a reference compound, spectrum from a library. That's because only spectra of identical compounds have identical fingerprint region. That's why we have the name fingerprint. It's unique for each particular spectrum. Otherwise, except for the fingerprint part, this usually provides very low information. It has very low information content. not much information. So we don't usually look for individual bonds that would be absorbing in this part of the spectrum. There are some that do, but we don't consider them to be particularly diagnostic, and we look at other parts of spectrum to identify individual bonds. Here is a summary of important absorptions in the two regions we just covered, between 3500 and 3100 inverse centimeters and 2000 and 1600 inverse centimeters. If you wish, you can pause the video here and examine this in more detail. And here are IR absorptions of various functional groups of various bonds. Again, if you wish, you can pause the video here and examine this in more detail. For each bond or functional group, you should know where it appears in the spectrum, at what wave numbers, and also intensity, whether it's strong or weak, and whether absorption band appears as broad or sharp. And now we're going to look at some sample spectra of organic compounds. So first, spectrum of 2,4-trimethyl-pentane. When you analyze this spectrum, you can see that there are no functional groups. If you look into a table and try to find functional groups, you won't find any. There's simply no characteristic absorption bands. The only absorption you can identify is the 3000 due to CH bonds, but pretty much any organic compound has it. The only conclusion you can draw from a spectrum like this is that you cannot find any functional groups. So either this compound has no functional groups, or you cannot see any. For example, there will be symmetrical functional groups like symmetrical double or triple bonds. And of course, this is an alkane. So to identify this compound properly, you would need information from other spectra like mass spectrum and NMR spectra. Then this spectrum of 1-hexene, and starting at the left, you can find there is sharp and relatively strong absorption band around 3100. That's due to hydrogen attached to sp2 carbons. And then there is weak and sharp absorption around 1650. That points to carbon-carbon double bond. So you would draw a conclusion that this is an alkene with at least one hydrogen attached to carbon-carbon double bond. This is 1-hexene, so that would be correct conclusion, but you can't really draw a conclusion this is 1-hexene. You can't tell exactly which compound it is, only that it belongs to class of alkenes. So for this you can see that IR spectrum provides some information, but there are limitations to it. And then 1-hexene. Now, starting at the left, we can find very strong, sharp absorption around 3300. So you would draw a conclusion that this is terminal alkyne. And that's also supported by the fact that around 2100 there is weak and sharp absorption. That's due to sp hybridized carbon. So triple bonds absorb in this region. Again, you would draw a conclusion this is terminal alkyne. You can't say which one it is, but again you would be correct that this is terminal alkyne. And in this case, we have another absorption around 300. In fact, there are two of them, two closely spaced weak sharp absorptions. That's characteristic of primary amine. So again, you can draw a conclusion that this is a primary amine, but you can't tell which one it is. Again, to tell which one, you would need more information. You would probably need mass spectrum and NMR spectrum. This is 1-hexene amine. Next spectrum is that of phenol. Of course, here we have hydroxyl group, OH. Note it's at 3300. It's strong and broad. Now this one is much stronger than usual OH group. Typical OH is about half or third of the size of this one. This one is unusually strong because phenol has only 5 carbon-hydrogen bonds. So CH relative to OH is relatively weak. Typically, organic compound has many more CH bonds compared to one single OH bond, and in relative terms, OH absorption appears to be much weaker in intensity. But nonetheless, from this example, you can see where OH group appears. And then Note between 2000 and 1600. Note those several weak absorptions. That's aromatic ring. So those are easy to miss, so make sure that you don't miss presence of an aromatic ring. Between 2 and 4 weak sharp absorptions in the region between 2000 and 1600. Next we have spectrum of 2-pentanone, a ketone, and in this case there is only one absorption, difficult to miss, right in the middle of the spectrum, around 1850, strong sharp absorption going all the way down. That's typical keto group, typical carbonyl group. And finally, here we have a carboxylic acid, hexanoic acid. So now you can see what hydroxyl group looks like when it overlaps with CH. It's actually really easy to miss, but you can see that if you pay attention to CH, it doesn't quite look right. And it doesn't because it overlaps with OH. And of course, in addition, we have carbonyl group around 1850. So 2 in combination point to carboxyl group. Again, you can only tell that it's carboxylic acid. To determine exactly which carboxylic acid, you would need additional spectral information from mass spectrum and from NMR spectrum. This completes our study of IR spectroscopy, and next we are going to look into NMR spectroscopy.